Hello, this is Mr. Mays. I'm coming to you in this pre-recorded session in the multiverse. It's a pleasure to have you here. We're going to get started. We're going to just talk through all the stuff that we messed around with on our introductory lesson, okay? So a lot of this stuff is not too complicated, not too deep, should be a pretty short video. But as you can see, I've already got us started out here. These are the 5 terms that we started off as our way of understanding data and conceptualizing statistics. It spells out CSOCS, as you can see adorably here on the left. And its constituent elements are context, shape, outliers, center, and spread. And real quick, I'm just going to go through each one of these, talk about its significance, what it does, and remind you of some of the examples we may or may not have gone over in class, just to keep it firm and sensible in your brain, okay? So starting with context. Context is incredibly important with all things in life, right? It's your background, it's what's going on. And it's any background. The way I like to frame it is I like to say any background info that clarifies the data set. Right? So what makes it clear what's going on in our data set? So an example I might give is something like the question, what's the most violent living thing? Right? And let's say we wanted to make a statistical study of that question. Well, we would have to stop and we'd be like, okay, well, wait a minute. Well, what does violence mean in this context? I mean, for crying out loud, you got to clarify that. Well, any background on what it is that term violence will mean for my study is going to be considered context. Even the concept of living thing, are we only talking about animals? Are we including like Venus flytraps and things of that nature? All of that would be considered context. Also, how many people you decided to interview about it or how many different species you decided to look at, right? Those would all be considered context. And anything, I'll put a hashtag for the number of things that you would read, and where you went, right? Oh, where did I find that information? What countries? That's all context, and it's super important, right? Because if we don't have all of that information, we don't have a good understanding. So for example, for violence, we'd probably look at number of fatalities caused by that particular living thing, right? And if I were gonna set that apart, I would probably just, number of fatalities. You see my delicious handwriting. I apologize profusely. I hope it's legible, but I'm glad I'm saying the words out loud too. For clarity. I'd say ask me questions, but it's not quite possible. So, moving on, we have shape. Shape, again, not too crazy a thing, but there are a lot of really cool terms that we can talk about when we look at shape, and we'll just review some of the ones that we looked at in class. Skew is a big part of shape. And remember, we talked about both left skew and right skew. And so really quickly, I'm just going to show you what those look like. This would be an example of a left skewed data set. And this over here would be an example of a right skewed data set. And I remember telling you, hey, listen, be aware. A lot of times people will mix up left skew and right skew. But it all has to do with what we call the tail. If the tail is on the left, it is left skew. If the tail is on the right, it is right skew. And I think of it this way because the tail is pulling the data away from being what we would call an approximately normal distribution. That was hideous. 10 points off to Mr. Mays for not knowing how to draw something. A normal skew or approximately normal skew, you can kind of see what I'm going for. No, it's not even a skew at that point, just a normal curve. Has no skew, approximately normal. And all the wonder that beholds. God, look at that handwriting. Okay, so we have the approximately normal, and then we have skews that are caused by, you can see me trying to fix this normal graph. Then we have the skews caused by data that pulls our everything, the whole conglomerate, to the left or to the right slightly. Okay, and those create our skews. Okay, and those things can tell us various things. So an example I often use is I'll be like something that's often left skewed would be something like lifespan, right? Where the majority of people live to be older aged. And something that would be right skewed would be, on the other hand, income, where most people don't make a lot of money and that a few people make an enormous amount of money. I love that I've reached a point where I've drawn so many things over these two skews, it's impossible to see them, but you saw them before, so you know what you're doing. Okay, some other things to keep in mind when it comes to the shape of our data. We have unimodal, we have bimodal, and we have multimodal. Multi is anything more than 2. Bimodal is 2, and unimodal, of course, is 1. Okay. And some quick examples on what those might be or how those might behave, right? If we're looking at, the median height of a human being, that's going to be unimodal, right? Anything where there's one definite norm, that's going to be unimodal. Bimodal, on the other hand, an example I sometimes give is when people say they're going to go on a diet, right? And a lot of people say they're going to go on a diet right around after New Year's and right around after Thanksgiving. Those are the 2 times when people make promises and then they don't keep them, right? So those are 2, key moments when people make a particular promise to themselves. They're going to do this thing, and we interpret that data bimodally, and understandably, that makes good sense to us. The other one that I really like to use for multimodal is the number of Google searches for how to cook a turkey. These tend to happen around Thanksgiving, around Christmas. I'll just say Christmas. And around Easter. Those are the times that people are most likely to need to cook a turkey and then to search it on Google because, let's be honest, nobody knows how to cook anymore. And so that's an example of something multimodal. And all of these shapes give us a lot of information. You'll notice in order for me to make these make sense to you, I have to give you all this background info. And of course, all these examples I give you, if you don't like them, you can always replace them with those of your own interest, right? The key thing to remind yourself of here is that the number of modes is important because it tells you where the majority of your data sits and it gives you information about behavior, right? You'll notice also with a lot of multimodal graphs, I want to put this on the record, that they will most of the time look clustered. Now, not always, but a lot of the time you'll have multimodal graphs that are clustered, where you have 3 different modes, and each of those is considered a cluster, and that's something to remind yourself of for your notes. And then the spaces in between, actually let me make those a different color. The spaces in between those clusters, I should denote that a little more clearly. The spaces in between are just called gaps, as obvious as you can make it, so it is. Okay, we have our clusters and we have our gaps, and that's the majority of what you need to remember for shape. We also need to remember, though, that there are 2 main kinds of symmetric data that we're going to be looking at this year for the time being. And those are approximately normal data, which we've just talked about. The example for which would just be a unimodal graph, where everything is sitting in the center, and there's no skew, left or right. And then, on top of that, another one is what's called uniform. A uniform data set or a uniform visualization is just going to be one where most of the data sits all around the same place. So here's what we would call a roughly uniform data set. So I'll say that's roughly uniform. And all that means is that every value I'm measuring here comes out, all the frequencies come out to the same amount of volume, right? And we should always remember that our y-axis measures frequency. All right. So we've gone through, we understand now context and shape relatively in depth. And now we're going to move ever forward. Outliers will be pretty quick. You'll notice context and shape are kind of the big ones that take the most time to talk about. Outliers, just data that's far away. from the center or from the rest. That's a Y. Away from the rest. The runaways, right? If I have like a dot plot going on and the majority of my data is like here, 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 and then we got this guy who's hanging out over here all alone, like me in high school. Just kidding. That data point would be considered an outlier. It's further away from the rest. It's really cool because soon we're going to find a mathematical way to determine outliers. There's a really cool rule that we often use in statistics to say if something is an outlier or if it's just an extreme data point that makes a skew. But we don't have to worry about that yet. We've all heard about outliers, so that should be pretty easy. Our center, I've said this a few times already because in describing, shape and spread, it's pretty easy to understand the center. But if I have data, right, and it looks like this center is going to be either the mean or the median. Those are the two things you should remember. We use the mean when our average is the best way to understand something, and we use the median when outliers are a concern. Outliers concern. I love that like half of the video note is just me scribbling like misunderstanding my own language. Like, look at this. Like, how can you even see that O there? Like, is it even legible? Okay, now we're going on a side note. We're going on a tangent. Every math teacher's favorite joke. All right, we're back on it. So that would be what our center is, where the mean or the median is. And why is that important? Well, that's where the bulk of our data sits. Everything else, though useful, allows us to better understand what's considered abnormal versus what is considered the norm. And then finally, we end with spread. And spread is really cool. We go in a lot of depth later on about what spread truly is. But what you should know right now is that standard deviation variance, interquartile range, and range are the main ways that we measure spread. Everybody, for the most part, should know what range is. It's your biggest value minus your smallest value. Interquartile range, we'll go over that in a while, but that has to do with standard deviation. And I'll show you that in a moment. We do that a lot with like box plots and things like that. But just understand that it's like sections of range, if you will. So we take a section of the data and we take the highest value from that section and the lowest value from that section. We subtract one from the other, and thus we understand the interquartile range for that section, okay? Then we have variance and standard deviation. Variance is standard deviation squared, and we do that to make it more extreme and to eliminate negatives. Why? Well, we will talk about that in a later class in more detail, but just understand that most of the time in statistics, and this is a good rule to know, we square things when we want to make differences more dramatic. So if the difference between two values is like 3, and we square that to get 9, we basically are taking that difference, 3, and in statistics, sometimes we want to amplify our differences so we can really understand how far apart things sit. Well, you will square those values. Also, in statistics, negative values just give you direction. So -3 difference between two values only tells me the direction I'm going, to the left or to the right. So just to get an understanding of that visually, if I were to take an approximately normal curve and I have my center, this is -1 standard deviations to the left, this would be 0, and this would be +1 standard deviations, right? This is to the right. And this keys in really well with standard deviation, which is the next thing we're going to talk about. So actually, let me highlight these values so it's clear. Oh no, that's my eraser, not my. Here, I'll do it in red. That makes more sense to me. We'll erase this, and we'll do it in red. Everyone likes red, right? Boom. -1. This will be whatever, -2. And this will be 0, and this will be +1, and this will be +2. And these are standard deviations. We'll talk about that in a second. But for variance, specifically, if we move to the negative, right, the difference between 0 and -1, even though it's -1, is actually just one chunk of data. And you'll notice that it's the same amount of data on the left as on the right. So we're looking at just amount of data in statistics. So the negatives only tell us direction. A standard deviation is where a certain amount of your data should lie on a graph. Or on a graph, I should say. So the rule of thumb that we often like to use is that on an approximately normal curve, if you move one standard deviation to the left and to the right, so when we say one standard deviation in both directions, so to the negative one and the positive one, 68% of our data should lie there. So all of this surface area here that I'm getting holds 68% of our data in a normal graph. So that's what a standard deviation means. So that means one standard deviation to the right, from 0 to 1 to the right, is 34% of our results. One standard deviation to the left, also 34% of our results. And together, it all holds 68%. If you're going to get wilder and you want to go 2 standard deviations to the left and 2 to the right, that, in effect, oh, I did that wrong there. It should go just to here. That, in effect, contains all of this, and that should hold about 95% of your results on a normal distribution, okay? If we are moving 2 standard deviations to the left and right, okay? And then, of course, if you divide that in 2, that will give you the understanding that basically like 40, what is that, 40, I should have this faster in my brain, 47.5% exists 2 standard deviations to the left, and 47.5 exists 2 standard deviations to the right. You can probably tell by my slow math processing brain right now, I am working on very little sleep. But for you, there is nothing I will not do, my student. Okay. So that's what standard deviations are. And what you should recognize above all else about a standard deviation is that standard deviations differ graph to graph. And what I mean when I say that is they are standard across all graphs. So the standard deviation used for one graph will be a different number than the standard deviation used for another graph. What's standard about them is the percentile that they represent. Right, so standard deviations will always have 34% within one standard deviation to the right, 34% within one standard deviation to the left, right? Always. But if my data is super spread out, if my normal curve is like this, and it turns out my values are way far apart, like this is 1, this is 5,000, this is 10,000, 15, 20, 25,000. One standard deviation, either way, is going to be a higher number because my data is further spread out. So that's why it's a measure of spread. Versus if we have much tighter data, like 1, 2, 3, 4, 5, or like when we did the measurements in class for different heights, that would be tighter data, okay? So the takeaway I want you to have on standard deviation for spread is that low standard deviation means tight data. Data that's close together, a close spread. And a high standard deviation, on the other hand, is looser data, right? It's wider. Okay, so those are our big takeaways when it comes to spread. I hope you've enjoyed listening to these notes. I super appreciate each and every one of you for coming through, or I guess just specifically this one person watching this one video as the cosmos continues to waver its way on and we further our closeness to colliding with the sun. You're a hero, you're a legend. Please ask questions if anything doesn't make sense to me by going in on Remind or shooting me an email. As always, it's been an honor. I hope I was at least vaguely entertaining. This has been Mr. Mays, signing off.